So we continue with our discussion from previous class. So in previous lecture, what we saw was that in a general problem basically being that I have an arbitrary shaped object of arbitrary dimension. We are not saying it specifically 2D. It's translating with a velocity u bar. And the fact that we are solving Laplace equation means that we can write down our potential as a series in terms of these various quantities that are known as multipoles. So there is a source, there is a potential dipole, and there can be other higher singularities. Now when you do a cylinder problem or you do a sphere problem, or for that matter you do any shape body problem which is translating, the source contribution will not be there. So we saw that source contribution being there implies that there is a net mass flux across the surface of the body. So because there is no net mass flux across the surface of the body, which is why there cannot be any source contribution. So the only contribution that you could have is basically dipole and higher singularities. Now for a cylinder and a sphere, the only thing that is there is a dipole. You don't have the other higher singularities. So just writing down what is your solution, let me just pull up, we had derived this in last lecture. So this is pi, the potential in 2D. So potential in 2D sphere was minus u bar a square cosine theta by r. Now if you do the same thing for 3D, you can repeat the same calculation. You will basically start by saying that there is a constant, and so your starting point is, you start with this, apply the boundary condition, and after all that exercise you will have a solution that will be minus u bar a cube cos theta by r square by 2r square. Okay, so the same approach, there is nothing that is different here. You have a potential to begin with, and the potential, you apply the boundary condition that the radial velocity on the surface of the body should be equal to the radial velocity of the body. That was the boundary condition. This is what you will get. So what this is telling us, and this is something which we are again repeating multiple times, that we are solving a linear equation, and this linear equation is with linear boundary condition, which means the general solution for the potential can be expressed as the translation of the body multiplied by some vector harmonic. This capital phi is basically some solution of Laplace equation. So del square phi is equal to 0, and what is it? It depends on the shape. So for instance, we saw what it is actually for the sphere problem. So for the sphere problem, the vector harmonic is minus a cube by 2r square and then nk, because u bar k nk is cosine theta u bar. Okay, that's the normal for the 3D sphere. Actually, I don't need to keep saying 3D, I'll just say sphere. And for a cylinder, you can read it out from there. It is minus a square by r nk. Right. So now this, even if you don't know exactly this quantity, you know that this is going to depend on the geometry. That whatever objects you are looking at, if you have an object that is, let's say, a spheroid, you will have some form of this. So right now we are not really interested in what exactly that form is. That particular quantity, the vector potential phi, is a function of the shape, the geometry of the body that you are interested in. But what we want to instead do is that can we use this and go forward and try to find an answer regarding the force the body experiences, because this is unambiguous. The fact that the solution of the problem depends, or the potential of the problem depends linearly on its translation, is indisputable. You cannot argue against it. You are doing a linear problem. So, if the body were to move with 5 times the velocity than its original velocity that you solve the problem for, your potential will be 5 times that value. That's as simple as that. Now, we are not doing a problem where the body is spinning. So, right now we are only doing translation, but you can imagine that if there was a spin component to it, you could have written down that in terms of angular velocity, there would be something else that will be there. So, we are not right now doing any kind of rotation of a body. So, we will just focus on this part and let us see how much we can make progress. So, we are keeping it as generic as possible and we will try to move forward from here. So, what is our goal? So, our goal is to find force on a translating body. So, I have some shape. This is the body that I have. Boundary is given by SP, and far away I have a region that I will draw which is S infinity. This is like some circle of a sphere of radius large r. This is moving with velocity u bar, and u bar could actually be now a function of time. I am not saying it has to be steady translation. Consider a point on this rigid body. This is a rigid body which is moving, and so I put a label which is x naught, some coordinate on the body. So, the definition of u bar is d dt of x naught is equal to u bar of t. That is just saying the statement of rigid body translation. I am not doing any rotation. So, this is all that is sufficient for me. Okay. Now, we need to find what is the force. So, the force acting on the body, the definition of force, and this is universal definition, it has nothing to do with potential flow per se, is sigma ij nj ds. You integrate the traction vector or the surface force over the body surface. That is all that we have to do. Now, we are dealing with an inviscid fluid. Okay. Since we are dealing with an inviscid fluid, sigma ij has a very simple form which is minus p delta ij. So, our life gets easier and the force is now minus sp p ni ds. Now, what is p? Here we use Bernoulli. So, we fall back to our favorite Bernoulli's equation, and Bernoulli's equation here tells us that p by rho plus half u square plus gz and plus dou phi dou t, because it need not be a steady motion, is equal to a constant. I am not going to be interested in any height differences. So, I am going to ignore the fact that may come due to buoyancy effects and all. So, for the time being I am just going to focus on this. So, I go back to my Fi, which was minus p ni ds. I substitute for this as minus half u square. So, it is minus rho half u square plus dou phi dou t ds, ni ds, which is rho half u square plus dou phi dou t ni ds. This is all over the body surface. Now, there is a constant here. Why did I not take in the constant? So, whatever is that constant pressure when integrated over a closed surface will integrate to 0. Right. If you think of like the constant being an atmospheric pressure or some constant value, if you integrate any constant pressure, normal force over a surface, it will be 0. And you also know this now from tensors that if P was a constant, integral Ni ds is the isotropic tensor of order 1, which is 0. This is something which you have also learned when you did tensors, right? That if you have to do this, this should be isotropic and then you get it to be 0 if you are doing it in case of a sphere. Otherwise, if you are doing it here as a force, the pressure basically being a constant value, you will not have any contribution. Okay. Good. So, now let us try to evaluate these quantities one by one. So, let us look at what is dou phi dou t. Now, dou phi dou t is related to the change in the potential with time. Now, what would bring about the change in potential with time? So, if you go back to your expression for your potential, you have to remember the potential is u bar k times phi k. Now, this phi k that I wrote down, if you just check what we had here for a sphere, I wrote down this potential here. There is a small r in the denominator. How is the small r defined? The small r is defined with respect to the center of the body, which means if the body is translating, that distance that you are measuring is actually varying with time, which means each of these quantities are functions of x minus x naught. X being any point in space, x naught being any point tagged on the body, right. The solution that you are finding solving a potential flow, even though we have not formally said this, the coordinate system was always stuck on the body. Even when we solved the problem for a body that was translating, when we said that the body was moving, at that instant of time there was a coordinate system that was stuck on the body, or that was coinciding, let us not say stuck, it was coinciding with the center of the body at that instant of time, even for when the body was in motion. At the next instant when the body moved elsewhere, if you have to find what the potential is, then you will actually now have a coordinate system that is coinciding with the origin of the body at that location. So, which means this particular quantity dou phi dou t will obviously have one term which is d dt of u bar times phi k, that is without any ambiguity, and then you will have another term which is dou t of xi minus x naught I multiplied with dou phi dou xi. So, what I am saying here is that I have a coordinate system where phi is a function of x minus x naught. So, when I do a time derivative, there is a dependence of x naught with time. This, if I say that phi k is a function of x minus x naught, when you take a time derivative of this, this will basically be time derivative of this multiplied by the gradient of phi with respect to your xi. Does that make sense? So, with this, now what we have here is k phi k. Now, this is something which we already know. Going back to, it was written in the previous page, which is the translation of the body. So, I will use k, it is using the same notation, and dou phi dou xi is basically the fluid velocity. This is basically the fluid velocity, this is basically the body velocity. So, the unsteady part of the velocity potential, its rate of change with time, is now uk ddt of u bar phi capital U bar small uk. Okay, so we now have more or less things that we need. So I am going to start plugging things, and we will do a little bit of calculation with this. So I will have Fi. So in the term involving dou phi dou t, that would be rho Ni ds evaluated over the surface. So this comes from the first term in dou phi dou t. So I am doing this. Then there is a second term which is rho Sp u bar k, the fluid velocity uk Ni ds. And then you have another term which is half u square Ni ds. That is the total force that any body is going to experience, which then it is translating with some velocity u bar. So now I will look at these two first in combination. So when I take them in combination, I will have half u square minus u bar k small uk Ni ds. So that's basically what I should have. So half u square Ni ds. All of these are over the body surface. I could write this now as an integral over the distance that is far away minus all that I have done is apply divergence theorem. So this is the body, this is the body surface. I have a distance enclosing, a surface that is enclosing the body. This is the volume between the body and that surface. So the divergence of half u square integrated over the volume is the difference of the surface integral over the outer surface minus the inner body surface. So I am just using divergence theorem here. So now let us work with the volume integral for some time. Now if you remember, dou xi of half u square, we have actually looked at this in when we did tensors, because dou xi of half u square can be also written as dou xj of ui uj dv. If you remember, the expression that we had was u dot del u was del half u square plus u cross omega, right? Now irrotationality means omega is 0, and incompressibility means this becomes divergence of uu. That is what I have done here. I have basically used the two ideas, that it is irrotational and it is divergence free, which allows me to write this particular term in this form. Now you once again apply divergence theorem. So now you are applying it the other direction, you are converting a volume integral to a surface integral. So when you convert the volume integral to a surface integral, this becomes, so this is all volume integral, this becomes S infinity ui uj nj ds plus sp ui uj nj ds. Now, I will combine these two, that becomes now half u square ni minus uj nj ds. Now, uj nj on the surface of the particle has only one component that would be non-zero. I can write it as u bar j nj, right? On the surface of the particle, the boundary condition tells me that uj nj, the fluid velocity's normal component on the body surface, should be equal to the normal component of the body's translational motion. That is my boundary condition. So, if I use that boundary condition, I can write this as u bar j nj ds. I can go one step further. I realize that u bar j is obviously a constant. So, I can take out of that integral. So, I have uy nj ds. Now, look at this particular term. This is an integral done on this surface which is far away. So, this has some radius capital R, where R is much larger than a typical body dimension. Now, how does u decay when we are at large distances? So, we went through this exercise. We said that the source will not contribute. The only term that will be there, the leading order term, will be the potential dipole. And we know that the potential dipole in 2D goes as 1 over r square. The potential dipole in 3D will go as 1 over r cube, right? Now, if you say that there is circulation in the problem, if there was circulation in the problem, then how would the velocity field in the 2D problem decay far away? It will be 1 over r. So, without circulation, it is 1 over r square. With circulation, it goes as 1 over r. In 3D, there will be no circulation. It will only be there in 2D. So, now you check each of these cases. The term inside the bracket is u square. So, in 2D, that term will go at least as 1 over r square. And how does ds behave in 2D with r? So, in 2D, this will be at least 1 over r square, and ds is, it's the perimeter in 2D, right? The surface area, that's for the two-dimensional circuit. So, that will go as r d theta. So, that integral in that particular case will decay as 1 by capital R in 2D, and so it will vanish. So, as you keep taking that s infinity to larger and larger distances, the integral, the first integral is going to vanish in 2D as 1 by the size of that outer region. In 3D, u goes as 1 by r cube, so it is a very rapid decay. So, u square will go as 1 by r to the power 6, and ds here goes as r square d omega, which means the integral will go as 1 by r to the power 4, and it will also vanish quite rapidly. So, in either case, the justification now we have is that this first integral is going to disappear in the limit of r going to infinity. So, what we have now is that the integral that we evaluated, the first term in that integral, which was half u square ni has now turned into u bar j ui nj, and the second term which was already there is u bar k ni uk ds. So, from half u square, we basically got u bar j ui nj, and there was already a u bar k uk ni. Okay, so we are almost done with our exercise. So we will write down now our force. So Fi is rho I'll take the u outside, k phi k ni ds over the body surface. And the second contribution is rho over the surface of the body. So that can be written as uj nj u bar nj ui. So u bar j nj ui minus u bar k uk ni ds. Now there is nothing special about calling them as j and k separately, right? So I will just use the same notation here. So I am going to just write it as u bar j uj ni. So the final expression for force is, there is a part that comes from its unsteady motion and there is a part which is there from even in the steady translation. So this is the force that a body is going to experience irrespective of its shape when it is translating with a velocity u bar. Now if u bar was a constant, which means steady translation, then Fi is rho u bar j sp u I n j u j n I ds. Now what is drag? Drag is the force that is along the direction of its motion. So Fi, if I take the component of the force along the direction of motion, if you want you divide it by the magnitude, then you get a unit vector. So then you have rho u bar I u bar j by the magnitude sp ui nj minus uj ni ds. Now what is this in terms of its order as a tensor and nature as a tensor? What is the order of that circled quantity? It's a second order. What kind of tensor? It's a second order symmetric tensor, right? If you switch j with I, you get the same answer. So it's a symmetric second order tensor. What about the term here? What is the order of that tensor? ui nj minus uj ni. This is also second order. And if you switch j with I, this becomes antisymmetric. So you have a second order symmetric tensor, you have a second order antisymmetric tensor, which are being double contracted, which means this is 0. So what you have shown here, without saying anything about the shape of the body, that if it was steady translation in potential flow, the drag should always be 0. So this is a proof of D'Alembert's paradox, which is as general as you can keep it, because typically when you try to prove these things, often the proof relies on using a restriction of 2 dimension, which is typically comes from something known as Blasier's theorem, where you solve the problem in 2D and show that drag would be 0 for a steady translation. This is just using the idea in terms of what will be the total force that the body will experience, and then eventually you conclude that the drag should be 0. Now, if there was no circulation, you didn't have any circulation that was there in the problem, then once again, if you look at that particular integral, so this particular integral, now you can use again a divergence theorem here, and you can take this to a large distance and show that this is applicable. You can write ui as dou phi dou xi, uj as dou phi dou xj. You apply divergence theorem and you will be able to show that this is actually the same as the integral valued at infinity. Now, how does u decay in absence of circulation? What is the decay in absence of circulation? So, no circulation implies that u in 2D goes as 1 over r square, and obviously in 3D there is no circulation, so it goes as 1 over r cube. So, now if you plug u as 1 over r square and ds is some r, or rather 1 by r square, and this is some r d theta, that integral vanishes in 2D and it obviously vanishes in 3D, which means if there is no circulation, both drag and lift are 0. There will be no lift also in the problem if you don't have circulation. But if you have circulation, so I am going back to that same expression, rho uj uinj ujni ds, which is the same as over a large distance uinj minus ujni ds. Now, if you have circulation, obviously this is only now applicable for 2D, then u for large distances goes as 1 over r. Now, look at this integral. The integrand is going as 1 over r. The differential element is going as r d theta, which means that will not be 0. It will have a finite answer. So, we will now write this out. If I try to now calculate what would be my lift force. So, if you know your with circulation, your potential that you have is kappa by 2 pi, or I think I have used gamma, right, gamma by 2 pi theta, and then there are the other terms. You have the next dipole term, etc. All those things are there. So, we are just looking at this particular quantity. So, gradient phi is gamma by 2 pi gradient theta. So, I will say that there is some object which is translating with a velocity, let us assume, in the x direction. So, for lift I want to compute the force in the y direction, because we know there is no drag in this problem. So, if I try to compute the lift, so it will be Fy rho, u only has an x component, so that is over j only takes a value that is 2, I is basically j has only value along 1 and I only has along 2. So, I will have I is going to be, this will be v, this will be nx, and this is u, and this is ny r d theta. Now, rho u bar, so v is dou phi dou y nx minus dou phi dou x ny r d theta. If I substitute in terms of theta, I get rho u bar gamma by 2 pi integral dou theta dou y, nx is cos theta minus dou theta dou x, ny is sin theta, r d theta. So, this is over 0 to 2 pi. This entire quantity dou theta dou y cos theta minus dou theta dou x sin theta, if you apply theta as tan inverse y by x, you are going to get as 1 by r. So, the final answer is Fy is rho u bar gamma by 2 pi 0 to 2 pi 1 by r d theta. So, the answer is rho u bar gamma by 2 pi into 2 pi, which tells us that doesn't matter what the shape of the body is. The body could be circular, the body could be elliptical, the body could be a square, body could be a more rough surface. If there is any arbitrary shaped body that is moving with a velocity u bar and there is a circulation associated with its motion gamma, it will experience a force that would be normal to its direction of motion, which would be rho u bar gamma. It's a very, very powerful result because it has no connection whatsoever to the geometry of the object. There is absolutely nothing to do with geometry here. It just says that I move with a velocity u bar and there is a circulation that I have. Yes, now there is a hidden bit information here. What is the circulation? Now, that is what we will come to in the next lecture, but at this moment, this particular point is something that is at the heart of a large part of development of aeronautics and aerodynamics, which is the Kutta-Joukowski theorem. That if you imagine this is the cross section of a long wing, so this is what is basically, you have an airfoil, so you are looking at a cross section. When you say there is an infinitely long cylinder is what we are studying, in a real problem, if you think of a long aircraft wing and you take a cross section, you will have a cross section. Obviously, it will not look like this, it will look something slightly different, but not focusing on the geometry, you are effectively looking at a quasi two-dimensional problem there. And what Kutta-Joukowski theorem tells us is that if this body was translating with a velocity u and by some mechanism it was able to generate circulation, it will create lift force. So, this is a very powerful idea and all of this is coming from potential flow. I am not trying to say that viscosity is not important here, because the next lecture we are exactly going to hit the nail on the head by asking where did the circulation come. We do not have an airfoil rotating, right? There is no spin or anything that is there. So, where is the circulation coming from? That is obviously not addressed yet, but the powerful point that it says is that if there is a circulation that is there in the problem and there is a uniform translation of this object, you are going to get a lift, which is a force normal to the motion. It's a really profound statement that you get, because we never used anything whatsoever. Think of what you have done. You have solved a nonlinear problem. You have not done any linear problem here. Pressure is nonlinear related to the velocity. You have not made any statement regarding the geometry, and yet you have come up with a statement on the exact force that the body experiences. So, with this I will close here, and then there are two more things to discuss. One is the part which I said was 0 by saying steady translation. This is again something that is very crucial. We found that drag was 0 when we said it was steady translation. You can already see that when u bar is not a constant, there is going to be a contribution to the force balance. So, this is what will come next, and finally concluding with the source of circulation. Okay. With that we will close here.